Welcome to this explainer. Today, we're going to completely break down the chemistry, the origins, and the real-world environmental impacts of sulfur oxides. Whether you're studying environmental science right now, or, you just want a much clearer understanding of the actual air we're breathing every day, we are going directly to the data. We'll trace these compounds all the way from their basic chemical origins right through to their tangible physical effects on our cities and our biology. Here is our agenda for the session. We'll start with an introduction to sulfur oxides, move into natural versus anthropogenic sources, look at their atmospheric lifespan in sinks, examine the physical and material impacts, and finally cover the effects on living organisms.
All right, Section 1, Introduction to Sulfur Oxides.
Okay, first things first. We need to establish exactly what chemical compounds we're analyzing today. When we talk about oxides of sulfur, or we just say SOx for short, we're primarily focusing on sulfur dioxide. SO2 is really the principal constituent of this entire group of pollutants. And at its core, this compound is produced during the combustion of sulfur-bearing materials. So think about common fuels like coal or oil that naturally contain these trace amounts of sulfur. When you subject them to the extreme heat of combustion, that sulfur bonds with oxygen in the air, and boom, you've got sulfur dioxide. Now, to give you a scientific baseline here, the natural background level of SO2 in clean, unpolluted air is extremely small. We are talking just 0.02 parts per million. That is a vital metric to keep in the back of your mind. It shows us that under normal, pristine conditions, our atmosphere holds literally just a microscopic trace of this gas. Understanding that tiny baseline is absolutely essential for recognizing when concentrations spike to dangerous levels. Moving right along to Section 2, Natural and Anthropogenic Sources. Let's look at where atmospheric SOx actually comes from. This breakdown usually surprises people. Contrary to what you might assume, a massive 67% of atmospheric SO2 comes from entirely natural sources, while only 33% is anthropogenic, meaning human-generated. Nature is actually the primary emitter here. But, as we're going to see very shortly, that definitely doesn't mean our human contribution is harmless. So what exactly is driving that 67% from nature? It's mostly two fascinating phenomena. First up, volcanic eruptions. Volcanoes forcefully eject these massive, towering plumes of sulfur dioxide from deep within the Earth directly up into the atmosphere. The second one is maybe a bit more surprising. It's the oxidation of dimethyl sulfate. This is a compound produced by marine phytoplankton, literally microscopic organisms living out in our oceans. Through these incredibly complex biological and chemical cycles, these tiny organisms are actually responsible for a huge portion of the global sulfur cycle. On the human-made side of things, our 33% contribution largely stems from two things. First, the combustion of sulfur-bearing materials, like the fossil fuels we touched on earlier, and second, the heavy industrial processing of sulfide ores. When we extract valuable metals like copper, zinc, or lead from the earth, they're often bound up in these sulfide ores. The smelting or processing of those ores releases significant amounts of SO2 directly into the local environment, and it tends to concentrate the pollution in very specific areas in a way that nature typically doesn't. Let's jump into Section 3, Atmospheric Lifespan and Sinks. So what happens to these molecules once they're released into the sky? Well, they aren't permanent fixtures up there. The atmospheric residence time for SOx is strictly between 20 to 40 days. In atmospheric science, residence time just refers to the average duration a molecule spends in the atmosphere before it's naturally removed. A 20 to 40-day window means that sulfur pollution is somewhat regional. It travels along with weather systems, sure, but it typically falls back down to Earth within about a month. It doesn't persist for decades or centuries like some greenhouse gases do. Now, during that specific window of time, a completely crucial chemical reaction occurs. The SO2 undergoes oxidation to produce SO3, or sulfur trioxide. And here is the real key to all of this. Both sulfur dioxide and sulfur trioxide are highly, highly soluble in water. This solubility is the defining characteristic that dictates their eventual fate. When these gases encounter water vapor floating in the atmosphere, they readily dissolve and they fundamentally change the chemical makeup of the moisture in the air. Because of this extreme solubility, precipitation acts as the primary atmospheric sink. It literally washes the pollutant out of the air as it rains. Now, while this is incredibly efficient at cleansing the air and returning our atmospheric concentrations back toward that 0.02 parts per million baseline, it basically just transfers the problem from the sky directly to the ground. Which brings us to Section 4, Physical and Material Impacts. When these soluble compounds mix with atmospheric moisture, they create sulfuric acid aerosols, and these aggressively attack our built environment. Just looking at the data, the impacts are severe. In archives and libraries, this acid exposure causes paper and leather to turn yellow and physically disintegrate. Over in construction and engineering, it massively accelerates metal corrosion, especially when the relative humidity is high. And perhaps most visibly to the public, it chemically eats away at carbonate building materials. This is exactly why gorgeous historical limestone and marble structures, which are super rich in carbonates, literally slowly dissolve away in highly polluted cities. Furthermore, on a macrophysical level, SOx combines with atmospheric smoke to produce thick, blinding smog. We're not just talking about an abstract chemical equation here. It becomes a choking, highly visible reality. The interaction between sulfur oxides, particulate matter, and humidity creates a dense smog that drastically drops visibility and creates immediate, severe public health emergencies. That leads perfectly into Section 5, Effects on Living Organisms. For us human beings, the smog we were just talking about is incredibly dangerous. It penetrates deep down into our lung tissue and causes severe respiratory harm. Because these acidic aerosols are totally microscopic, they just completely bypass our body's natural upper respiratory filters. Once they get deep inside the lungs, they cause acute irritation, they can exacerbate asthma, and they can even lead to long-term chronic respiratory diseases. In beyond human health, we see some really severe botanical damage as well. Short durations of very high SO2 concentrations result in fatal leaf necrosis. Now, necrosis literally just means the death of living tissue. So if a plant is exposed to a sudden high spike of sulfur dioxide, the cellular structure of the leaf breaks down rapidly. It leaves these harsh, dead, discolored patches. And of course, the plant completely loses its ability to photosynthesize effectively in those damaged areas. Conversely, even if the concentration is quite low, prolonged exposure is still going to slowly poison the plant. This results in these distinct brownish-red or bleached white areas all across the leaf blade. This is chronic damage. It highlights that SOx doesn't just destroy biology in massive, concentrated, visible events, it can subtly degrade the health of whole agricultural crops and natural forests over time, even at levels that might not instantly trigger human respiratory distress. Let's wrap things up with Section 6, Final Summary and Review. Let's review the core life cycle we've mapped out. The crucial takeaway here is that while SOx definitely has major natural origins and a relatively short atmospheric lifespan, its transition into soluble sulfuric acid makes it a highly, highly destructive force to both materials and living organisms before it finally washes away. We've seen how it forms from combustion, how it travels on the wind for up to 40 days, and how its high water solubility means it literally rains acid down upon our cities, into our lungs, and across our crops. I want to leave you with this final thought to really analyze. If nature already pushes the atmospheric baseline so incredibly high, just how delicate is the balance we hold with our 33% anthropogenic contribution? Our environment comes equipped with natural sinks, like precipitation, perfectly designed to handle the output of volcanoes and phytoplankton. But by forcefully adding that extra 33% through our industrial processes, we risk completely overwhelming those natural sinks, effectively transforming life-giving rain into a corrosive force. Thank you for joining me in this explainer. Keep questioning the chemistry of the world around you.